working on product and quotient rule. Just to remind you what they are. If you want to find the derivative of a function that's made up of two distinct functions multiplied together, then you can use this rule here. It's called the product rule. On the other hand, if you want to do one divided by the other, you can use this fella here. And it's called the quotient rule. And really what we're doing is, for the most part, just getting practice at doing them, right? The more functions you do it to, hopefully the better you get. We've done a fair number. There's not too many weird things, but you know, there's always something floating about. Let's do a version of 11. And I've picked 11 because of style points. You know, when I use that term, I just mean write the answer in as nice a format as you can possibly get it. And this one is one of those situations where the style points is actually more awkward than you might think at first sight. If I'm going to differentiate that, I hope you would all say, I need to turn things into fractional powers. Great. I'm going to differentiate a square root. That's no good. I got to change it to x to the half. And so now I can identify the top function as f and all the stuff on the bottom is g. And then I've got my formula. And the derivative is, I'm going to do the abbreviated version. I mean, it's the same formula without the x's. Now, if you differentiate the top, you get 1/2 x to the negative a half times the untouched bottom, which is x to the half plus 3. Subtract the untouched top, which is x to the half, and the derivative of the bottom, which is actually that guy, because the derivative of 3 is 0, and then the whole thing is the bottom squared. Are we okay so far? A bit ugly, but it's pretty straightforward as well. Okay, it's all about style points. It's all about making this pretty in the mathematical way. What do you think I should do next to the top line to get me closer to the best version of this answer as we could? No ideas? What would I do with this top line?
Did you distribute?
Yeah. So this guy times this guy gets you a half. This guy times this guy gets you 3/2 x to negative a half. And remember, I'm taking away both of these. So this guy times this guy gets you negative a half. And we got a little bit nicer answer. They cancel. And now I'm left with that guy. Now, if I turned this x to the half into the square root of x, and this x to the negative half, it would end up being 1 over the square root of x, which is really not that pretty. Is there a different way of writing this expression that takes care of this negative a half power and makes it a little bit prettier? Can you think of something you could do to a negative half power that might make it look a little bit nicer?
Write it
Question?
as 3/2 times the square root of x.
I didn't catch the last part. If you could say it again.
Write it as 3/2 times the square root of x.
Well,
Like
this.
sorry.
If you meant that, I agree with you, because that's the right thing to do. Now, let's see if they can maybe fill in. Isn't a negative power the same thing as a positive power on the bottom? Now that is where the square root came from. That turns into square root plus 3 squared. And that 3/2, well, there's the 3 and there's the 2. So this fella is considered the correct answer. Now here's a wrong answer. Wrong in the sense that it's not 100% correct. You could have done so what I've done here is I've just rewritten this as that guy. Now, when you look at that guy, it should look kind of awkward and clunky and not right. Can you see it doesn't look quite as nice as what happened here? And you're going to have to deal with the fact that in Calculus 1, there is a lot of algebra where you spend 1 line differentiating and 5 lines of algebra, either getting into a form that lets you differentiate or after you've differentiated, getting the answer to look as nice as it can. And that's really the big skill thing. Nothing there. They're pretty good. I'm just scanning through one, see what we can come up with. No, that's good. Okay, here's 19. In this case, it's going to be cube root of t on the top and a very innocuous t minus 9 on the bottom. Okay, I need to differentiate that. It's definitely going to be a quotient rule. How am I going to rewrite the cube root of t so I can differentiate?
T to the 1/3.
Agreed. I think that part we're probably comfortable about now, right? You know, you have to have fractional powers. You can't leave things as square roots or cube roots. Now, this fella here looks a bit weird, but unfortunately, isn't the function itself called f of t? So its derivative is called f dashed of t. But for the sake of my formula, don't I have to call the top f and the bottom g? Now, what that means is, I don't think it'll really be a big deal. Aren't there 2 kinds of f going on here? There's the original f, which represents this, and then there's the working f, which represents this guy. You okay with the fact? I mean, they could have called that p of t and it would have saved a whole load of trouble, right? But that's just a placeholder. That's the f and g that we're really interested in. So let's see what we get. If you differentiate that guy, you get 1t, reduce the power by 1 gets you negative 2/3. Leave that guy alone. Subtract, leave the top one alone, and differentiate the bottom, which is just 1. And the whole thing on the bottom gets squared. When you're looking at this question, and you're looking at making it look pretty, it's quite common, isn't it, that you're going to FOIL these things out or distribute, whatever it happens to be. So this guy times this guy gets you 1/3 t to the positive 1/3. This guy times this guy gets you negative, what on earth does that get? Negative 3t to the negative 2/3. And this guy at the end gets you negative t to the 1/3. Oh, this one's going to be messy. Check it. Yep. Check it. Yep. Check it. Yep. Right. I'm now going to collect like terms. And I have 1/3 take away this guy. So what that leaves me with is negative 2/3 t to the 1/3 power, take away 3 lots of t to the negative 2/3 power. I'm going to write this top line on its own. That is probably going to be one of the ugliest situations you're going to encounter. A negative fractional power, a positive fractional power, a nice coefficient, an ugly coefficient. It's pretty much got everything that you could to screw this up. Oh, and by the way, how about 2 negatives thrown in just for fun, right? I'm going to work on this guy and I'm going to turn him into the best version this thing, this expression can be. So here's my first. Are you okay with me pulling out a rather unnatural common factor called negative 1/3? Are we okay with that? Can you see I'm pulling out a negative 1/3? That leaves 2. Pulling out a negative 1/3 gives you 9. Now, the way you can check it is if you multiply these together, do you get back to that one? And if you multiply these 2 together, do you get back to that one? And so it is valid. And the last piece is going to be the kicker in the tail. Both contain a power of t. That means I can pull out a power of t as a common factor. Now, you're used to doing common factors when one of them's t squared and one of them's t cubed, right? Or one of them's t to the 5 and one's t to the 4, right? You know how to do those guys. Isn't the rule that when you have 2 different powers of t, you can pull out a common factor and it's the smaller of the 2 powers is the one that you do? You can pull out a common factor even in weird cases like this. You have a t to the 3rd and you have a t to the negative 2/3. The common factor here is the smaller of the 2. So the common factor is that guy. Now that one gives you +9. Now the last little piece of the puzzle. I have t to the 3rd here, and I am pulling out a common factor of t to the negative 2/3. Essentially, I'm subtracting this power from a 1/3. Something really cool is going to happen. What do you get if you take a 1/3 and you subtract negative 2/3 from it? So I've got 1/3 and I'm subtracting negative 2/3.
Wouldn't you get 1?
And so, boom. I have now factored the heck out of that expression. I've got a negative 1/3. I've got this ugly negative 2/3 power, but at least I got a 2t plus 9. Right, it's looking a little bit prettier. Now, 2t plus 9 is good. Stick a negative, bring down a 3, and make that guy on the bottom.
Wait, wouldn't it be 2/3? Because if you subtract negative 2/3 from a 1/3, that's still one
No,
negative.
say it this way:
1/3.
1/3 subtract negative 2/3. That's what I said.
Oh,
1/3.
add. Okay, yeah.
And so that's essentially adding. Now this guy is coming downstairs, and yeah, I'm happy with that. So back to the original question. See this ugly guy in the top? He's turned into a negative 2t plus 9 with a 3t to the 2/3 underneath it, and then t minus 9 squared. So that stuff got me that, and the t minus 9 squared is still there. Now I'm looking at the WebAssign answer to that, and they are being really nice to you. They are accepting that, but we don't accept that. Because in mathematics, there's a number of rules and style points, and one of them is make it look like the original. So there's the final answer. In this question that we've just finished, more than 3/4 of the work was pure algebra. I mean, the only real line that was calculus was there. Right when I differentiated. So I hope you're getting the idea here that you're really in an algebra class and you're learning some tricks that you're probably not aware of or done a lot of practice of. And things like how to simplify by unusual common factors, for instance. That's a very common strategy when square roots and cube roots are involved. You end up doing things like this quite a lot. Well, hopefully that one didn't scare you too much.
It scared me.
No, nothing there, nothing there.
I'm
Oh, I'll
thoroughly
just do
scared.
this question. Sorry.
I said, I'm thoroughly scared. I don't think that would have been intuitive for me to do all that. So I guess I'll just practice those a lot.
Yeah, you're going to get practice. Well, I won't say a lot because I'm just scanning through. There are only about 3 questions where anything as messy as that happened. So we're talking at the tail end of experience, right? It's not your typical question. It's much more like your advanced question. So it's like you're doing your advanced driving test, right? You'll be able to drive quite well 99% of the time, but occasionally you're going to have to hit some weird stuff. Maybe I should try and find another one of those. But the only one I saw that was as bad as that was the one I just did. I'm looking in case I missed one. Okay. Hard to tell what's going to happen until after you've done it. Yeah. No. Question 11 is an easier version of that one. It doesn't come out anywhere as bad. But I saw another one. Is it Hayden? No. Okay, that was your one and only shot at seeing it. There might be another one and I've missed it. There's a square root one in question 11, but it's a little bit easier than that. So there's no much point in me doing that. Now where is that one I was going to do? 23. Yes, there we go. This is a new tack. This is a different situation. AX plus B over CX plus D. Well, what makes this one a bit different? Well, it looks to me, hopefully it does to you, that there's an awful lot of other letters floating about here. But only one, well, God in Himmel, that's an X. Only one of them is in fact the variable, it's the X. So what about the A, B, the C, and the D? They are constants, right? They're just considered normal numbers. So when I do a different derivative of this guy, I don't really have to do any preparation. Those guys there are going to be my F, And those guys there are going to be my G. So I just have to be careful about differentiating. If you differentiate AX plus B, all you get is A. Agreed? Like 5x plus 3, you just get the 5. Leave the second guy alone. Take away, leave the top alone. And differentiate by this guy. So if you differentiate CX add D, you just get C. Style points is still important. Distribute ACX plus AD, multiply by C, ACX, take away BC. And it looks like the A cancel, that's nice. AD, take away BC, over CX add D squared. So, I mean, that was just getting practice at differentiating when there's a lot of constant terms floating around. Before I leave this one, that derivative tells me a little bit about any linear fraction function. So if you take any fraction in the universe that's made up of a linear combination of x's and numbers like 5x plus 2, and on the bottom things like 3x minus 7, right? You take any function that looks like that, this is its derivative. First things first. Do you notice that the top is just a combination of one number, take away another number? You agree? Which tells me then that this function typically will never be 0. Won't AD take away BC end up being 7 or minus 42? Which means that these functions never have hills or valleys. Whatever they do, they don't have a hill or they don't have a valley. And that's for every combination of them, except I guess the trivial combination, the AD take away BC happens to be the number 0. I have no idea what that would look like, but evidently, if that did happen, I know what it looks like. If it did happen, the AD take away BC was 0, right? Can you imagine you found a combination of A, B, C, and D that made that 0? Then the answer would look like this, wouldn't it? Which means the derivative would be 0 all the time. What kind of function has a 0 derivative for every single value of x?
A horizontal line.
Yeah. Now, I don't know if it's horizontal at 5 or horizontal at 4, which probably now makes sense to me. If you make the top one a multiple of the bottom one, won't they just cancel out and you'll get f of x equals 3 or f of x equals a third? Right, so if you make this a multiple of the bottom, so the top's 2x plus 4 and the bottom's 4x add 8, right? I bet you this would be equal to 0 in that case. So that's what they're telling me, is that this will never have a hill unless you get the top one as a multiple of the bottom, in which case you don't really have a fraction function at all. You just have a horizontal line, because function will be equal to a number. That was quite a nice one. Okay, what's left? Well, there are two things that we haven't covered. Multiple derivatives. In other words, finding those kind of guys. And equation of tangent lines or normal lines. Right. Well, actually, we know how to do both those things. It's not that they're brand new. We're just going to do it to situations where the product and quotient rule are involved. So let's jump into a question like this fella. Suppose I'm being asked to find the first and second derivative of this particular function. Not that difficult to do, it's already set up. If you differentiate this guy, you get 3x squared. We'll leave that one alone. Leave this guy alone and differentiate that guy. And look for style points. Okay, what kind of style points could we do for that question? How could I make this pretty?
You can factor out an e to the
And your dog agrees. What else?
An
She's
x
right.
squared.
An x squared. And then whatever is left is that. And unintentionally, we have generated a problem. That answer is perfectly fine. But if I'm going to find the second derivative, don't I have to differentiate this? So the unintended consequence is, have you noticed that this is made up of 3 things multiplied, not 2 things multiplied? It's got an x squared, it has an e to the x, and it has a 3 plus x. So we have to find a workaround for that. I'll show you one version of it. Let's do a generic version. I know what the rule for 2 things multiplied together is. It's that rule, right? There is a product rule for 3 things being multiplied. And it's all to do with symmetry. Has anybody, and it's really just an intelligent guess, has anybody want to have a shot at what you think the product rule for 3 things multiplied together would be? Bearing in mind it's going to look similar to 2. I mean, you might be wrong. Probably will be. If it was me guessing the first time, I'm sure I was wrong.
Would it just be like really similar to that equation where it'd be like H, or it'd be like F, G, and then H, like the last one?
Okay,
Like the
well,
grade
which
third.
one? Which we need a derivative, don't we?
Yes.
Which one do you want to give it to?
So for the first one, it'd be F,
Okay.
and the second one would be G, and then the third one would be H.
If you were the first mathematician to see that, you've just created a product rule that works for 3 functions.
Yay.
You see how symmetry, just seeing patterns. Now, if you were doing it, and you had to publish it, you'd have to prove it, right? You'd have to go into the limit as h tends to 0 kind of technique and prove it, in general. But that's the answer. Doesn't it have an elegance to it? It's not clunky at all. Doesn't have a, well, to me, isn't that kind of beautiful? And there's a flow to it. Right, so back to this guy. I'm going to call this fella F. I'm going to call this fella G, and this piece H. And so the formula is going to be F dashed GH plus F G dashed H plus F G H dash. Okay, so if you differentiate the first one, you get 2x, and then you leave the other 2 alone. you leave the middle one alone. You leave the first one alone. You differentiate the middle and leave the third one alone. Leave the first one alone, leave the second one alone, and differentiate the third. Now we have to make it look pretty. Let's see if we can factor anything out. If you look at these three terms, is there anything that you can pull out as a common factor from each term?
X e to the x.
Nailed it. Now, let's look at each one and suck out an x and an ex and see what's left over. In this case here, won't there be a 2 left over and a 3 plus x? Would you agree? If you take out an x e to the x, there's a 2 left over and a 3 plus x. Well, why don't I just multiply them while I'm at it? And that's where the 6 plus 2x comes from. You happy about the first one? Okay. Now, in this one, I'm going to pull out an x e to the x. A little bit messier. If I use up 1x and all of this e to the x, isn't there an x left over and a 3 plus x? Right, so there's 1x left over and a 3 plus x. So I might as well multiply them while we're at it. So 3 in the x and the x in the x. Now the last one, if you pull out an x and an e to the x from this, isn't there just an x left over? Can't I just collect like terms now? So what have I got? I've got an x squared, I've got this guy, and this guy, so it looks like a 6x plus a 6. I'll have a quick scan. Yep. I was looking for factoring, I can't, so I'm finished. Okay. So first derivative, piece of cake. Second derivative, we had to create a new rule, how to differentiate 3 things that are multiplied. And we had to pull out some slightly messy common factors. Are we okay with that question? Do you feel comfortable about the process? Again, calculus was just one line. Wasn't the algebra of the thing most of the work. So let's look at a first and second derivative where there's a fraction involved. So this is 26. Top is F, bottom is G. I don't have any real issues with that. Quotient rule now. F dashed G, take away F of G dashed over G squared. Right, if you differentiate the top, you have 1, leave the bottom alone. Subtract, leave the top alone, and differentiate the bottom, you get 2x. All over the bottom thing squared. Okay, I'll see what I can do to make it look as pretty as possible. And basically, not an awful lot. Oh, God in Hamel. There's really not an awful lot I could do except to, distribute it a little bit and collect like terms. The x squares didn't come out very pretty either. You might be tempted to think that you could factor the top, I guess you could pull out a -1, but it doesn't really help, so I'm not going to do that. And if I pulled out a -1 as a common factor, I'd be left with x squared plus 1, not x squared minus 1, if you were thinking that. And so nothing good is going to come out of that. This guy is f, this guy is g. But we have to differentiate it because we're going to find the first and the second derivative. And so we now have to break a rule. Normally in style points, don't you make things look as pretty as possible? Right, that would be the answer. But when you want to differentiate something, don't you sometimes have to make them ugly just so you can differentiate them? Because don't I need to differentiate x squared minus 1 squared in a few seconds from now, don't I? I'm going to have a g dashed. If I leave it like that, aren't you going to have a problem with differentiation? So what I'm going to do here is not typical, but it was necessary, is I'm foiling that out. And the reason I'm doing this is to make the bottom, what's the word I'm looking for? Differentiable, right? Something I can differentiate. Do you see I kind of needed to do that or I'd end up getting myself into kind of deep water later on. So now we can do the second derivative. And it's going to be f dash g, take away f of g dashed, all over g squared. Right, if you differentiate the top, you get negative 2x. If you leave the bottom alone, you get x to the 4, take away 2x squared plus 1. Subtract. If you leave the top alone, you get negative x squared minus 1. And if you differentiate the bottom, 4x cubed minus 4x. Whoa, just squeeze that thing in. Now I'm going to do a couple of cosmetic things here. Do you know this guy in the bottom? Wasn't that guy before I foiled him out. So this guy squared is now this guy to the power of 4. Do you see how I tidied up the bottom? This guy was x squared minus 1 squared, and now if you square that, you get x minus 1 to the 4. Now that was kind of nice. What on earth is going to happen to that top?
I can't read the far right term. Is that
This far right term,
4x? Yeah.
it's 4x cubed, take away 4x.
Okay.
So what do you think I'm going to do this entire top messy bit?
Distribute.
Yeah, could distribute. But I'm not. And would distribute work? Yes, it would. Can you trust me? It would be the biggest, ugliest polynomial you've probably ever seen in your life. So I am going to do this. Isn't this fella here, right? X squared minus 1 squared. If I take this negative and I work it on this one, can't I turn this into x squared plus 1? And this guy here, I'm going to pull out a 4x, and that's going to leave me with x squared minus 1. So I've taken this guy and essentially distributed the -1 to get a much nicer looking answer. I've taken the 4x cubed minus 4x and sucked out 4x as a common factor. So I now have negative 2x, x squared minus 1 squared, plus 4x, x squared plus 1, x squared minus 1. Okay, look at the top line. Look for common factors. Can you see anything in these two expressions that I can pull out as a common factor?
2x.
Right. I think I heard 2x, okay. Anything else?
One instance of x squared minus 1.
Agreed. That's pretty much everything I can see as well. So let's see what's left. Used up, one of these used up, and a negative. So I've got a negative left over, and I have an x squared minus 1. If I distribute them through, you get that. Are you happy with the negative x squared minus 1 getting you that? Now, what else have I got? I've used up a 2, so I've still got 2. I've used up that, and I've used up that. So what have I got left? 2 of these. So that's 2x squared plus 2. This and this combine to give me x squared, and this combines to get me plus 3. Do you see by the avoiding, the most natural thing to do would be just to multiply this out? What I've managed to do is factor it quite nicely. And now I've noticed something that very rarely does happen. Doesn't happen at all, virtually. Do you see anything that I can do to simplify it just a tiny bit more?
Would the 2x minus 1 cancel one of the bottom 2x minus 1 terms?
Oh, the x squared minus 1s?
Yes, I'm sorry.
I got what you meant. This guy cancels out one of them. So what you're left with is 2x, x squared plus 3, and now you're reducing this by 1. I don't think you'd get any prettier an answer than that if you tried. But that was some heavy duty algebra. Now, there are two ways to tackle this question, and the one that you gave earlier, Ethan, would actually work. You foil that damn thing out. The problem with it is you end up with a massively ugly polynomial, and you will be able to pull out 2x as a common factor. And that would leave you with a polynomial that would look really weird. And this isn't, well, actually, I can tell you what the polynomial is. This is what you would have ended up with. Right, so when you foiled the whole thing out, you would have ended up with pulling out a 2x, and that can be factored. Right. It can be factored as an x squared plus 3 minus 1. And then you would have ended up with this. So it's not that Ethan's method would have been wrong. And maybe for some of you, that might have been a more direct approach, even if it was uglier to do it. So I'm not poo-pooing the idea that you could just distribute all that. And there'd be a lot of things dying, right? But you would be left with something like 2x to the 5 plus 4x cubed minus 6x, right? That's what would be left alive once you foiled it all out and collected the terms. And then you have to work on this by pulling out a 2x, and lastly, recognizing that this actually factors. So if you could do that, go for it.